Hi guys, welcome to another one of my lectures on light, and today I will be looking in depth at the properties of light, and we'll be looking at reflection. We'll be examining briefly refraction. We will also be looking at how light can be diffracted and interference for it to occur. So when I talk about light, I'm talking about literally light from either a luminous source or light reflected from a non-luminous source. So light is represented by an arrow, where a single arrow represents a ray of light. Now if I have multiple arrows that sort of diverge, they form what I call a divergent beam. And in the same way, I could have rays of light which all point to one thing, which is called a convergent beam. Now, when I talk about light, I am talking about a form of energy. So I normally like to use where I have a little bubble and I look at the main concepts associated with light. So it is a form of energy. I could look at it as it can travel in a vacuum. I could also look at light as it has a speed of 3 by 10 to the 8 meters per second in both air and in a vacuum. It is made up of all of the colors of the rainbow, Roy G. Biv. I could also say that light could undergo the properties of reflection. It can be refracted. It can also be diffracted, or I could have interference taking place. Now, when I talk about light, one of the foremost things is that light has a dual nature. So what do I mean by light having a dual nature? Light can be made up of particles, and this is according to the corpuscular theory, or I can conceptualize light as made of waves. Now, if light is made up of particles, then these ideas were brought forth by people like Max Planck, Albert Einstein, even Newton. And it conceptualized light as being made up of packets of energy called photons, right? And this concept was further reinforced using the photoelectric effect, which is something that we look at the CAPE level. Now, if I were to examine light as a wave, anytime a form of energy is transported as a wave, it must exhibit 4 primary characteristics. It must be reflected, it must be refracted, it must undergo diffraction, and it must undergo interference. Right? So now when we talk about light, let us look at the concept of reflection and refraction. So when I talk about the reflection of light, there are 2 laws that are considered. So reflection is a concept where a light ray, right, and again, it's a single ray I'm showing you here, hits a reflecting surface, and what happens with that surface is that it simply bounces off the surface. So in order to determine what rules govern its reflection, I draw a normal, which is a perpendicular line to this reflecting surface, and it's imaginary. And the purpose of the normal is that it allows me to determine something called angles of incidence and angles of reflection. So the angle between the incident ray, which is this ray here, and the normal will give me this angle here, which is my angle of incidence. And similarly, this ray, which is reflected off the surface, the angle between that and the normal is my angle of reflection. And the first law is that the incident ray, the reflected ray, and the normal all lie on the same plane. And I could also associate with the second law that the angle of incidence is equal to the angle of reflection. Now, one of the concepts of refraction is basically that light rays can pass from one medium to another. So what that simply means is that, let's say I have a ray. So we're going to go back to the concept with a normal, and then you have, let's say, glass. So when we talk about light, you want light to penetrate a medium. So you cannot consider a translucent or even an opaque material, because then the light will simply be reflected. It will not be allowed to penetrate. So we consider primarily for refraction to be transparent surfaces, so transparent materials. So here we have the ray going from glass all the way to air. And because we consider that glass is more dense than air, because it's a solid, so the molecules tend to be more compact in that lattice arrangement, air has more spaces because it's a weaker, almost negligible force amongst the molecules. So it's therefore less dense. So what you find is that when the ray passes into air, it is going to move faster. So the velocity in air is greater than the velocity in glass. So the ray refracts away from the normal, and then the angle of incidence would increase as the angle of refraction. So the angle of refraction is greater than the angle of incidence. Now if I consider the reverse direction, let me show you a normal first, right? And I have my ray going from air all the way to glass. Remember, the velocity in air is greater than the velocity in glass, right? Now my ray will bend towards the normal. So here my angles of incidence will be greater than my angles of refraction, because as the ray is bent towards the normal, that angle tends to be smaller, right? Now another property I want to bring up is something called the refractive index. Now, the refractive index is a property of these transparent materials, and it is denoted by common n. Now, the concept of the refractive index is that it tells us the extent at which refraction is occurring. So here, if you are going from medium 1 to medium 2, then there is a ratio of the refractive index of medium 2 to medium 1. So if you go back to the diagram, we examine factors of speed and density, and that determines the extent of refraction in terms of, is the ray bent away from the normal or is the ray bent towards the normal? And in so doing, I would have determined angles of incidence and angles of refraction. Now we want to introduce another variable which does determine how the ray behaves. So you might find that the refractive index of air is 1, and the refractive index of glass is 1.5, and the refractive index of water is 1.33. So the faster it travels, the lower the refractive index is, right? So that as well determines the extent of refraction. Now, the second law of refraction is what we term Snell's law, and it looks at a ratio of the sine, right? A lot of students just indicate the angles. It is the sine of the angles of incidence compared to the sine of the angles of refraction, right? And if you go in your calculator, sin, it's a function, and sine of an angle gives you a number, right? Because in essence, it's a ratio, right? So when you look at the sine of the angles of incidence and refraction and you divide it, it will give you the same number. What I mean is that if you have a ray going, let's look at an example, right? So let's say I have a ray going from glass to air. Based on what I told you, you would expect that ray to bend away from the normal, not so? So let's say I have theta I being angles like 30, 40, 50, 60, right? And I then get my angles of, okay, let's not use these. All right. So let me say, and I get whatever I get for theta r, whatever my angles are. I'm saying that the ratio of these angles to whatever the corresponding angles of refraction are will be a constant ratio. And that ratio tells us the extent of refraction occurring when the ray leaves glass and enters air. So again, I could use it for if I am going now from, let's just say, if I am going from air into glass. So my ray will refract towards the normal like this, right? So what you will find is that when I determine my angles of incidence and my corresponding angles of refraction, for each angle, my values of sine theta I over sine theta r is going to give me a constant value. So what is that constant value? The constant is in fact a ratio of the refractive indices or the velocities, or if when we do waves, into the wavelength, right? And the constant is indicated by N12. N12 tells you that a ray is leaving medium 1 and entering medium 2. So in this case, medium 1 is air and medium 2 is glass. So when my ray leaves air and then it enters into glass, it will bend towards the normal. And I would have a certain angle of incidence and a corresponding angle of refraction. And if I find sine theta I over sine theta r, then the number I get will be a constant value. Why? Because even if I change my values of incidence and refraction, I am still leaving air and entering glass. So my media are constant. I am leaving air and I am entering glass. And when I get that constant value, right, that constant, it tells me the extent of refraction taking place as well. And that brings me to my second law of refraction. So Snell's law says for a ray traveling from medium 1 to medium 2, the ratio of the sine of angle of incidence to the sine of angle of refraction is constant regardless of all values of theta, right? And we could use this ratio to indicate the different values. And again, the constant is 1, 2. The first law, tells us in refraction that the incident ray, the refracted ray, and the normal all lie on the same plane. Okay. Now, in the next video, I'll be going into more depth in the calculations involving Snell's law. The last thing I want to look at in this video is the concept of light in diffraction and interference. And if you recall, diffraction, right, I can represent my light as a series of plane wavefronts where the space between is lambda. So here I can have maximum diffraction of light occurring by having circular wavefronts here. Now if the spacing d is the same as the wavelength of light, I have maximum diffraction taking place here. And this was deduced by Thomas Young in Young's double slit experiment. So what he did was he had a double slit and the spacings here d would be the same as the wavelength, right? Because you want maximum diffraction. So if I consider light as a series of plane wavefronts, I have diffraction occurring at each gap. And what will happen is that as these diffracted beams interfered with each other, they produce something called fringes. And you had bright, then you had dark, then you had bright, then you had dark, then you have bright, then you have dark. So this alternate pattern of bright and dark fringes is what we term a interference concept, where these would only occur if you have constructive and destructive. Now, when we look at another video on waves, you would see that the solid lines represent crest and the space represents trough. So here, where I have two solid lines intersecting, that is a result of constructive interference, which is how when I refer to light, I see a brighter spectrum. And then when I have a space and a line, for example, like here, I would have destructive interference, which is simply darkness.